here's just a little overview of what you've already learned. And we talked about how what we perceive is the light that's not being absorbed. So all these colors are being absorbed and blue's not. So we perceive it as blue. And usually the wavelength that you want to use on a colorimeter or a spectrometer is orange. It's the opposite of the color wheel. Now this doesn't always hold true, and if you played with the PhET simulation you would see it's not always perfect, but in general that's the way it goes. And then I put some formulas on here. We're not really going to use this too much. Here it says power, and that was intensity, so you saw an I0 on the other one. And then we went through transmittance and absorbance. So if I had a colorless liquid in there, I'd have 100% transmittance and no absorbance. Percent transmittance is how we do transmittance. Absorbance is based on some other numbers that don't have units. That's to do with optical density. So the numbers percentage, this is in percentage, it won't equal 100, okay? And now we're going to look at Beer-Lambert's law, which is A equals, oops, you don't see that, which is A equals ABC, okay? In physics you might see A epsilon LC. But basically, absorbance is going to equal the molar absorptivity. If it is absorbing more of the light, it's going to have a higher molar absorptivity. Times concentration times the path length. And remember, the path length is that cuvette, that little cube that has the sample in. In general, this cuvette is usually 1 centimeter. And that becomes important because if I graph absorption versus concentration, and that would be cut off here, we usually don't do it at higher concentration. Okay, we're not going to deal with that in our class. If I do that, the slope equals our molar absorptivity if I have a 1 centimeter cuvette, okay? And down here, I just rearranged this so you can see that absorptivity divided by concentration equals molar absorptivity. This is our path length, and our path length is 1. So it works out like that, okay? And now, what you really need to understand is what a standardization, a standard curve or calibration curve is, okay? We use this a lot, not just in Beer's law, but it lets us determine unknowns. So let me show you how that works. Here, this is any sample. We could call it copper sulfate. We could call it anything, but it's just one sample. And if I make this sample at many different concentrations and I measure the absorption, I will get this straight line, okay? And because these are known quantities, I can now take an unknown, and you could even tell by color that my unknown would be less concentrated than our most concentrated sample. And if I take the absorption of that unknown, and let's say the absorption is 0.2 of my unknown, and I go over, I can find the concentration was somewhere around 3 milligrams per milliliter. Okay, so our standard or our calibration curve is a curve that covers anywhere an unknown might be in between 0 to the most concentrated. And then I take the absorbance of my unknown and I look on my curve and I figure out where my unknown is. So just again, if my absorbance was, say, 0.4, of course I'd be taking a really nice straight edge and doing this better, but it would be somewhere around 5.25 milligrams per milliliter. And that's what our standard curves do. And again, this is a lab technique we do not just with Beer's law, but with some other things, okay? And now this slope is going to equal the molar absorptivity, okay? If I have a 1 centimeter cuvette, okay? Otherwise, I'd have to take the slope and divide it by whatever my cuvette was, okay? Molar absorptivity divided by path length, which is B, okay? But here my B is 1, so my slope equals my molar absorptivity. So that's something that they might test you on, is to find your unknown from a standard curve, okay? They also might ask you some questions about some information on the path length and what wavelength you want to check. These are not on your list, so unless they give you these formulas in a question, it probably won't be on there. And you also need to understand that if I have 100% transmittance, I have no absorption. As my absorption increases, my transmittance goes down. So today you're just going to finish off this worksheet right here. And I talked about doing some other spectroscopy on Friday, but I think I'm going to tie in a review with some more Beer's Law in there. Call me or text me if you have any questions. I'm here to help.